Let's apply Newton's laws to analyze an Atwood machine. Here we have an Atwood machine consisting of a rope running over a pulley with two objects of different masses attached. The pulley we're going to treat as frictionless, and we want to know if we release mass 2, what will its acceleration be, and also what's the tension in the string connecting the two masses. I'm going to show you how to do this by drawing a couple of different free body diagrams. There are more ways of solving this problem than this, but this will give you some powerful tools in analyzing situations with more than one body. We'll start by saying there are two blocks that matter, and since we want the tension, we need to have at least one free body diagram that has the tension in it. I'm going to start by doing a free body diagram of block 1, which will look like a block with mass 1. Let's make it a little bit bigger so we can fit mass 1 in there. And then we'll have some forces acting on it. We'll have my y coordinate will be acting up, and we'll have a force of tension in the rope pulling up on it, and then it will feel the weight of itself dragging it downward. And we would expect that it would accelerate upward. So the acceleration of block 1, we expect, since it's lighter than block 2, it should probably accelerate upwards. Let's go ahead and note that this is 2 kilograms from the problem statement. And this one is 4 kilograms. Next, we'll do a free body diagram of block 2. Here we'll have a block, mass 2 in there. It will also have a coordinate with y positive going up. We will then have tension pulling up and mass 2 times gravity acting down. Here we would expect that this would accelerate downward. So we would expect that my acceleration 2 would be down. Let's go ahead and write our Newton's second law for each of these situations that says that the sums of the forces, in this case only the y direction matters, so I'm just going to skip to writing the sums of the forces in the y direction, are equal to the mass times the acceleration. And here we can write an equivalent statement for block 2 based on its free body diagram, where this will equal, here since I'm assuming the acceleration is going downward, this will be negative m2a2. So I've already taken account of the direction there. Now, what are these forces? Well, tension is pulling up and m1g is going down, so it will be tension minus m1g is equal to m1a1. And here you'll similarly have tension minus m2g is equal to minus m2a2. And this is the same tension because it's in the same rope. So the pulley just redirects the tension over the rope, or over the pulley, I should say. Looking at these, we can ask what things do we know and what things do we not know? Well, the things we don't know are tension, that's fine, that's something we're trying to find, and acceleration 1 and acceleration 2. The things we do know are mass 1, gravity, still mass 1, mass 2, gravity, still mass 2. So we have 3 unknowns and only 2 equations. We need some other way of relating A1 and A2. Let's go ahead and try combining these equations to see where we can get before adding in a relationship between A1 and A2. So I'll solve this for tension by adding m1g to both sides. So we get the tension is equal to m1g plus m1a1. And over here, we'll do the same thing and get the tension is equal to m2g minus m2a2. So far, so good. I now have tension equaling 2 different things. We can set those equal and combine these 2 equations. And this will give us m1g plus m1a1 is equal to m2g minus m2a2. But we're still stuck with 2 unknowns. If we had just one unknown, we could solve this equation for that unknown. Here, if we assume that the rope doesn't stretch, maybe I'll be explicit about this. So assume the rope doesn't stretch, what that means is now the acceleration between these two will be the same. And maybe we could have started with that and made our life easier. Here I'm being explicit about it. So in this case, my acceleration 1 is going to equal my acceleration 2. And we'll just go ahead and call that A. And that's true because acceleration 1 is positive up, acceleration 2 is positive going down. So I've chosen a sign convention that's compatible with me being able to say that these are directly equal. If I had said acceleration 2 was positive going up, I would have had to say they're equal to a negative here, and then it would have been fine either way. So as long as you're consistent with your choice of sign conventions, things should work out. So with that, let's go ahead and plug that in to what we were just doing. And we can say that M1G plus M1A is now equal to M2G minus M2A. So now we have one equation, one unknown, where that unknown is A. We'll go ahead and try and solve for this by moving all of the unknowns to one side. So I'm going to move all of the things with A on it to one side and move everything else to the other side. Here, that means I can subtract M1G from both sides. And we can add M2A to both sides. And when doing that, we end up with M1A plus M2A is equal to M2G minus M1G. This seems like a perfect time to factor to make things look a little bit nicer. And this says that A times the quantity M1 plus M2 is equal to G times the quantity M2 minus M1. We can now divide both sides by this combined M1 plus M2, and this tells us that my acceleration should be G times M2 minus M1 divided by M1 plus M2. So far, so good. We'll plug in the things that we know. 9.8. Sometimes I say 9.81. We'll do 9.8 meters per second squared. And then here we've got 4 kilograms minus 2 kilograms divided by 4 kilograms plus 2 kilograms. When we plug all that stuff through, we get a final acceleration of 3.27 meters per second squared. And when I want to write that as a vector quantity, now it depends which one I'm talking about. One's going to be going up, one's going to be going down. So I can say that my acceleration of block 2, which is what was asked for, is equal to that magnitude, 3.27 meters per second squared, in the direction down. Or we could say it's negative 3.27 meters per second squared in the j-hat direction. So we've got the acceleration. We're just left with finding the tension. So for part B, it asked us to find the tension. Luckily, we have expressions over here that we can just substitute back into to find the tension. Let's go ahead and do that and say, just picking one of them, tension is equal to M1G plus M1A1, which remember is just equal to A. And so when we plug in values for this, we have 2 kilograms times 9.8 meters per second squared, and then plus that same 2 kilograms, so maybe I should have factored here to make my life a little bit easier, but we'll just press forward at this point, 3.27 meters per second squared. And evaluating that, we get a tension in that rope of 26.1 newtons. Now this is a force, but this is an internal force in the rope, and whether it's up or down depends on what part of the rope we're considering. And in fact, as it goes around the pulley, you would expect it to be going around the pulley in some way. And since it's an internal force, actually, it depends also, am I talking about the force as it acts on the bottom part of this rope here? Or if I cut it there, the force as it pulls down on the top part of the rope, right? So for tensions, we generally just say, well, it's in tension and the direction is axially along the rope. One last thing is that we can double check this work by going back and looking at this other equation that we had and substituting in our values there and verifying that we get the same tension.